Our aim is 11.4 z-scores and area. Now, most data does not lie solidly on the lines of deviation as we saw in our bell curve. Most data lies within these boundaries. So how can we determine how many deviations away a point is from the mean? We use this by determining the z-score. And we can determine the z-score with the following formula. You take your given value of that data set, you subtract it from the mean, and you divide by the standard deviation. So now let's look at an example. On a standardized exam, the scores are normally distributed with a mean of 300 and a standard deviation of 40. Find the z-score of a person who scored 240 on the exam. So here you may even want to sketch a picture. It's up to you in order to get a sense. So 240, we know, will fall below the mean. So your deviation is going to be negative. So we plug in 240 minus 300 divided by 40, and we get negative 1.5. Now let's look at a second example. Tyler earned a score of 45 on exam A and had a mean of 53 and a standard deviation of 5. He is about to take exam B that has a mean of 400 and a standard deviation of 50. How well must Tyler score on exam B in order to do equivalently as well as he did on exam A? So first we're going to determine his z-score. And his z-score for the first exam was negative 1.6. So Tyler scored 1.6 deviations below the mean. So now we're going to plug that z-score into exam B. So if his z-score was negative 1.6 for exam A, what score would he have to get on exam B in order to retain that? So for the other exam, Tyler would have to score 320 on exam B in order to get the same, to be in the same deviation. So percentile. The percent of the population less than the data point is used to determine its percentile. So in a normal distribution, the 50th percentile is located at the mean or 0 deviations away. This is also the median. Notice it's your halfway point, so its percentile is 50%. Right there, you've done better than 50% of the other data set, or the other points in this data set. So finding the area. We can use our graphing calculator to determine what percentage of our overall data falls within a given range. So in our third example, at a local restaurant, the amount of time that customers have to wait for their food is normally distributed with a mean of 16 minutes and a standard deviation of 4 minutes. What percentage of customers have to wait between 9 minutes and 27 minutes to the nearest tenth? Notice how I've highlighted certain parts here because that will be important for us to determine the area. And when I mean area, I'm talking about the chunk of our bell curve that we would need to determine the percentage for. So in order to do this, we have to calculate our cumulative distribution function, or your normal CDF, in order to find out what percentage would lie within a particular range. So please watch the following video. So let's take our last example and let's determine the area or the portion of our bell curve that is covered within that range. So in order to do this, we're going to hit second vars, and we're going to hit number 2. Now, if you do not see these items listed in this manner, that's okay. you'll probably just see normal CDF with an open parenthesis. So I want you to enter in those numbers, just like these that we're going to fill in, but just add commas after them and close the parenthesis. You'll get the exact same answers. So our lower bound in this case will actually be 9. So I'm going to clear this. I'm going to put 9. Our upper is 27. Our mean, or mu, is 16. The standard deviation of 4. And we're going to paste that, hit enter, and then we hit enter one more time. So you'll notice here, some of you might see this in your calculator, might start it off like that. You may want to jot down in your notes that the first number is your lower, the second is the upper, the third is the mean, and the fourth is the standard deviation. So we hit enter, and we get that, oh, we were asked to round it to the nearest tenth. So here, what percentage? So here, rounding this to the nearest tenth, it's 95.7%. Imagine if we converted this decimal into a percent, that would be 95.7%. So, okay. So here, this is just an outline of it. If you ever have issues converting from decimals to percents, just move your decimal space 2 spaces over to the right. Now, of note, should you need to find the percentage that includes the tail ends of the bell curve, you have to choose a number for your lower upper bar that goes beyond all possible beyond all possible minimums or maximums in order to get an accurate percentage. So for example, if you have to find the lower bound, and you know, like one of the smallest numbers you can have is 300, when you're putting it into your calculator as a lower bound, just to make sure that you haven't made a calculation error and that your lowest possible number is something like 290, you may want to make your lower bound lowball it and say 200 as your lower bound. And the same goes with your upper. You can think of it, for example, as a test. If you wanted to figure out what percentage what percentage of the population got a test score of 85 or higher, and the highest is 100, you may want to make your upper bound 120. The 120, it won't have an effect because it's not a possible or reasonable outcome on your bell curve. So those numbers will zero out, but just make sure it makes sure that you've covered all possible options. So normal distribution with population size. Once we discover what percentage the data lies in within a given range, we can determine how much of the data falls within the given data set. So in this example, the amount of time a certain brand of light bulb lasts is normally distributed with a mean of 900 hours and standard deviation of 35 hours. Out of 105 freshly installed light bulbs in a new large building, how many would be expected to last between 870 hours and 950 hours to the nearest whole number? Here, we would put the exact same values into our calculator. We would find the normal CDF, and we would get the following proportion. Now, with that, we take the 300 and we multiply that by that proportion. And we get that to the nearest whole number, approximately 202 of those light bulbs will have that range.